forward to that. We're talking in 411 about just how interesting it is. Like, this is a real biohack sort of thing, right? So the Moderna and the Pfizer they're hacking our cells. They're injecting code into our cells to reprogram the cell so that the cells start to produce these pieces of spike protein that the coronavirus has and then emit them from the cell. Like we really have just reprogrammed the cell to create something that it wasn't going to create before. And I was like, what else can we do? Like, can we program to create insulin or to kill cancer cells, or like what are the implications of this new messenger RNA therapy? It's pretty cool. And then I got scared because I was reading about Moderna. It's a Cambridge company right across the river. They've been around since 2010. They've had 9 failed products. They've never had a successful commercial product. This is their very first one. And it happens to be an untested, untried, weird biohacking sort of technology. Is like, oh, yeah, what could go wrong? What could go wrong? Yeah, I know, Gabe. It's like, I know. I try not to go down those dark doors. So weird. But I mean, I understand. I'm not a virologist or a cell biologist, but I kind of understand the mechanisms that it's using. It's like, it makes sense to me what they're doing. It's just getting to that point. It's crazy, just crazy. Yeah, the Vax was in the works before, absolutely, Susaritha. But now, like, now that we've seen like that it kind of works, like, as who just said, oh no, the funding is going to be crazy. Look for a lot of startups around this coming up, right? I guess my real concern is that, like, no one's ever done this before. All these are new products, like new ideas, and like we don't know what it's going to do to us 5 or 10 years down the road. Who knows? Like, I don't know. Maybe I'll tell better jokes. All right, so let's pop into this. This took the full time last time. Oh, anyone know where this is? That's the Dead, of course. Where are they playing? It's here. This is 1970, November 1970. Not Morris. This is in Sargent Gym, which was down toward Aganis, that Nickerson Field zone. Yeah, November 70. They played here. The funny story about the show was I wasn't there. I was in 5th grade, but the Student Government Association put the show on, and for some reason they decided that the perfect opening act for the Grateful Dead was a troupe of trained chimpanzees. So there was this like weird circus act with chimpanzees that happened before the Dead came on. Just really bizarre. Thank you, Student Government Association. And then, like, it's a small arena, right? So it's torn down now. It was really small, and everyone on campus wanted to go. No one had tickets, and so everyone just showed up and milled around, and was partying and so on. And the rumor is, the story is that Jerry Garcia himself opened the back door, the backstage door, and let everybody in. And yeah, it just became even more crazed after that. So anyway, that's the time that the Dead played BU. And the Allman Brothers played town a couple of days before that. So it was, what a perfect time to be in the music scene back in the 70s in Boston. Watch the Allmans and then go watch the Dead. Geez, oh Pete, that's a time machine one. And there aren't really good tapes of the show. Like most shows have fairly decent tapes. This one, not so much. But what we can hear of the show, it was a killer show. Like, they were just on fire. Must have been the chimpanzees. All righty, let's talk about VM. Oh, it's not concepts. We want something else. Concepts. Where's the other one? That's not it. Hang on, don't panic. Where's my kernel stuff? Really, I was just looking at it. Are you kidding me? Hang on, I'll go find it. Kernel. Oh, I just changed the title page. Sweet. All right, here we go. So just a quick recap of stuff we talked about on Tuesday. So we talked about virtual memory on Tuesday, sort of from a conceptual standpoint. Virtual memory, like, it solves so many problems. The biggest problem it solves is that we just have limited physical memory on any machine. Like, there just isn't ever enough memory. And so we can't just map processes directly into physical memory. Remember on Krish, probably tomorrow, I've just been up to here prepping for this stuff. So I'll try to get it out for you tomorrow. Yeah, so like, remember on Tuesday we looked at like the simple view of memory with, just physical memory and a CPU, and we're just like addressing directly into that memory. It's just not possible with these big multitasking operating systems. There are just literally hundreds of processes that want to run. They all need, like, they just can't all fit into memory. It just doesn't work. And so virtual memory fixes that problem. It, it has the side effect of giving each process like this beautiful, clean, contiguous space that looks like real memory to the process. We know now that it's virtual memory, but it starts at zero and it just, the cells move up, one by one, all the way to the top. It's just nice, clean, contiguous memory. It's an illusion to the process, but it's a big, big win because, like, it's protected, right? It's like, hey, process, here's 4 gig of memory, like, have at it. And whatever it needs to do with that memory, it can. So that's a big deal too. We can also think of virtual memory as a cache for disk, especially programs on cache. When a program starts up, for example, we can just essentially read pages of that program into physical memory and map them into virtual memory. If I need, if there's a page that I hit that isn't in physical memory, I can just go grab it from virtual or from disk and pull it in. And so I can use virtual memory as a disk cache essentially, but not like a disk cache for data, a disk cache for the program itself. The program is represented actually in very similar fashion as it's going to appear in memory on disk. It looks kind of the same, and I can just pull those pages in, drop them into virtual memory, and then eventually they're going to show up in physical memory too. So it's just a really, really nice system. And virtual memory's, I don't know, it's been around since the 50s, I guess, but not like the 50s, 60s. People were playing around with this idea of virtual memory, but it was pretty limited. It wasn't really until I think the 70s, like early 70s, that really virtual memory hit its pace. And once that happened, like, there was just no turning back. Everybody uses virtual memory now. So Windows, Unix, Mac, all of them, like IBM ZOS, like, they all use virtual memory for this because it's just so obviously good. Now, this doesn't come at with no cost, right? Like, there's a lot of stuff that happens to make all this appear so clean and contiguous. Like, there's all these tables the kernel has to use. There's all this figuring out of, is something in memory? Is it not in memory? Do I have to get it from disk? What if memory runs out? Like, what do I have to do then? There's all these things that have to be taken care of. But the expense is, even though it's high, is relatively small given the benefits that we get. So that's why we're talking about virtual memory as a cache. It's a cache, right? So we can use cache semantics. So we can think of in a cache, does something need to be replaced? Because caches are usually limited space. What happens if I need to insert something into the cache, but it's full? I got to remove something. What am I going to remove? I don't know. Like, I might have a cache policy like least recently used. The least recently used page, the one I haven't used for quite a while, that's the one I'm going to replace because I haven't used it for a while. Odds are I'm not going to use it anytime in the future. Just to get it out of physical memory and stick a page in there that is going to get used. We can also think of, since we're talking about caches, we can think of the idea of a cache entry being dirty or clean. A clean cache entry is data in cache that represents what's on disk. So the two pieces of data are identical, whether it be instructions or data, variables that the program's using, whatever it is, they're identical in memory and on disk. That's a clean page, hasn't been modified. Versus a dirty page is one I modified the information in memory. Now it's different than what was on disk. I've got two copies and they're different from one another. I got to take care of that pretty quickly, because what I don't want to happen is like lose that page in memory. It's got data that's been updated. I need to somehow get that information back to disk. So we have to deal with that too. The kernel's going to, it just keeps all of these structures. There's so many tables and structures that the kernel has, and they all live in, remember this piece up here? This is the picture we've been using all along, kind of the process view of memory. Up here in this salmon zone where it says kernel virtual memory, that's the 1 gig space above the 3 gig down here, so it's 4 gig altogether. So that 1 gig on top is reserved for the kernel, and that's all going to be the tables, all of the data structures that the kernel's holding to make virtual memory happen, along with all the other stuff it needs to, all do all the kernel work. That has to happen too, but that all lives up here at the top of memory in that top gig. And again, we're pretty much just talking about 32-bit systems. It's 4 gig from top to bottom of this memory chunk. All right, so we're going to move pages into pools. Unix actually doesn't do this. Linux, for example, doesn't have the notion of a page pool. And it was so weird because I was working on this slide deck over last weekend, and I'm reading the book, right? CSAPP, we're in chapter 9 of that book, and it's really thin on virtual memory. And I'm thinking, why isn't he talking about pools? Like, pools are all over the place. Why aren't we talking about them? And then I remembered that Unix doesn't use them. And I was like, why am I thinking about page pools? Like, if Unix doesn't use them, and I remembered that way, way back in the day, I'm talking the 1990s, I worked at Digital Equipment Corporation, and part of my early job was I was a course developer, and I wrote the systems courses for our operating system, VMS. Well, VMS uses page pools to manage its paged memory. And it's like, oh yeah, that's where that comes from. For some reason, like 30 years, stuff is popping out of my head. Oh yeah, that's how that works, and this works this way. So I'm kind of filling in the details that the book doesn't talk about. And then it's like, oh yeah, Windows. Like, that's why Windows uses pools, because what happened was Dave Cutler, I mentioned his name a couple of times, I think. Just Dave Cutler. So Dave Cutler was the architect on VMS. VMS was Digital's virtual memory system. So that was the first big commercial virtual memory-based operating system, and Cutler was the architect for it. And he used this idea of pools of pages, mainly for performance reasons. But then Cutler left Digital and went to Microsoft, and he worked on Windows NT. Architect for both operating systems. So, when Cutler left Digital, he took all of his knowledge with him, and that's why NT, and then following on Windows, uses this style of pooled pages to manage memory. The WinNT is funny. So I got time for a really short story. So you remember the movie 2001: A Space Odyssey? And HAL, the computer, I'm sorry, Dave, I can't do that. That one with the glowing red light. So HAL was a takeoff on IBM. They were just kind of poking IBM a little bit about their computers. And it was because, like, if you look at HAL, HAL, the next letter up from H is I, the next letter up from A is B, and the next letter up from L is M. So it was a takeoff on IBM. So when Cutler loved the movie, and when he went to Microsoft to work on Windows, so he had worked on VMS, right? So the next letter up from V is W, the next letter up from M is N, the next letter up from S is T. So his project at Microsoft was the WNT project, as a kind of a spoof on VMS. It was one better than VMS, right? It kind of stuck. Like, everyone started talking about WNT, and they started calling it WinNT. It's like, like they had to come up with a name that matched the acronym. So they backronymed it, Bacronyming is when you start with the acronym and you come up with words to match the letters. So it became Windows. This is how they marketed it for several years. Windows New Technology is all they could come up with. Windows NT, next new technology. Anyway, that's my Dave Cutler story. So silly. And actually, he did the same thing to us at Digital. So there was our console language, the language we used to run the computers, Cutler designed it. And so it was Dave Cutler language, DCL. And we couldn't use Dave Cutler language in our materials. Like I was writing courses on it. I couldn't use Dave Cutler language in our courses. So Digital came up with Digital Command Language, which I thought was pretty clever. I love all these weird little history things. I didn't work directly with Cutler. I worked I worked with his group. We were porting VMS to, we were porting Windows NT to Digital's Alpha platform, an Alpha chip, similar to Apple's M1 chip, same sort of idea. So we're porting NT to our Alpha chip, and I had to work with Dave's technical team to sort of document what they were doing. Never actually met Dave, though. All right, anyway, sorry, I was like lost in history. Back to pools. So think about virtual memory and what we're doing, like what we talked about on Tuesday. We're taking that virtual memory space, this stuff, and anytime that the program as it runs needs to access like an instruction or something, that instruction has to be in memory. If it's going to work with data, the data has to be in memory, right? And so we're going to take pages of memory from disk, and we talked about like a page being 4K bytes, for example. So, you know, it's a big chunk of bytes, 4K. We're going to take a 4K page from disk and move it into the process's virtual space so that it can see it. Well, that means it has to be in physical memory also. And so to do that, we looked at page table entries on Tuesday, and there's nothing fancy about it. I've got a page number, page 10 or whatever. I'm going to move it from disk into memory. Well, the page table entry for this process, if it's on disk, I've got a little bit, one bit, the valid bit, and it tells me whether the thing is on disk or in memory. If the valid bit is 0 and I reference that instruction, it's on disk. I got to go get it and stick it in memory. So I go and page it in to physical memory. And then all I really have to do is put an entry in the page table that says, oh, it's a valid page now, it's in memory, and it's at this physical page so that I can go get it. So I'm working with pages. If memory's tight, especially, as I'm paging stuff in and out, paging something out typically means I'm going to write it to a page file on disk. That's a really expensive operation. Like going to disk at any time is going to take a long, long time, relatively speaking to the CPU. CPUs are really fast, right? So I want to avoid going to disk if I can. So what I can do instead is take those pages as I'm moving pages in and out of the process. And we talked about locality of reference also on Tuesday, which meant that as the program's running, it tends to run instructions kind of in a local zone, like, you know, in 100 bytes or so. Like it's just running this bunch of instructions that are all on the same page, right? As it sort of progresses through the program, now it's going to move into the next page maybe. I'm going to page that thing in. Well, that first piece, like I kind of don't need it anymore. I'm not really using it much. So I can just page it out of the process. Paging it out means that that page of physical memory I can use for some other process at that point. You know, I'm essentially freeing it to the operating system. Well, if I write that page to disk, A, I got to write it to disk, which is going to take a while. B, when I need it again, I got to page it back in from disk. Again, that's going to take a while. So why don't we cache them instead? I'm going to take pages that are being released by a process and place them in a cache. That cache is called the page pool. And there's two flavors of this. The paged pool, this one, the paged pool means those are pages that can move in and out from disk, But as I free a page up, instead of writing it directly to disk, I'm going to put it in the paged pool. When the kernel needs a page of memory, it's just going to go to the page pool and say, hey, is there a free page of memory that I can use? Oh, there's one right here. And then just assign that page through a page table entry to a process. So it's real fast. It's a memory operation at that point. Really, I'm just twiddling some bits on a page table entry. So that's a win, right? Like that's a performance win. There's also a set of pages that are never paged. That's the non-paged pool. The non-paged pool are assigned usually to the kernel. So these are things like kernel structures, the page tables, like there's stuff that we don't want to write to disk ever because we need it constantly and it's just really expensive to go and have to get it from disk. So those are all marked non-pageable. They tend to be, just kernel stuff. And they're all gonna live up here. So they're all gonna live here in this kernel memory. So those are the two pools, the paged pool and the non-paged pool. That's a little bit of a misnomer. It should really be the non-pageable pool because I can't page those out. But the paged pool I can. So that's a nice little cache of pages, and these all just live in memory. It's just a cache that the kernel keeps. And eventually, if memory's tight, the paged pool is going to shrink and grow, right? So if memory's getting a little tight, I'm not going to keep so many in the pool because I need that memory for other stuff. But then if memory is not very tight, I can keep a whole bunch of pages in the page pool. So that's the page pool. In the paged pool, pages are all either going to be dirty or clean. We talked about cache semantics, right? So a dirty page is one where the data's been changed on that page. It's different than what's on disk. That's not a good situation. If I've got two watches, I don't know what time it is, right? Oh, it's 2:12. Oh, it's 2:14. Which one's right? I don't know. So eventually I need to update the page on disk so that it matches the one in memory because it's been changed. That's a dirty page. I don't want to do it all at once though. So, I mean, one way to do it, of course, is when I'm going to page something out, instead of putting it in the pool, if I see it's dirty, just write it back immediately to disk and be done with it. But if I've got a lot of dirty pages and I'm paging stuff all the time, it's a performance problem. It's gonna take a lot of time. So I can just leave them marked dirty and have a separate pool for them. I got a dirty page pool, clean page pool. If the kernel needs a page of memory, first place it's gonna look is the clean page pool because those are unmodified. They're available to anyone. Just grab a page out of that pool and assign it. The dirty stuff, I'm gonna have to periodically flush those back to disk. So flushing just means I'm gonna write that data back to disk so that the memory version matches what's on disk. And again, I don't wanna do it all at once or every time rather for performance reasons. So I'm gonna wait some period of time. And actually in A1, I just keep remembering stuff from 30 years ago, writing the stupid VMS courses. It's so weird. Memory's so weird. Like, why do I remember that? But there's a setting in the operating system, which is the percent of modified pages that you can get to before you have to write them all back to disk. So let's say you had 100 pages in the pools and 20% was your threshold value. When I got to 20% of the pages in the pool that were dirty, then you essentially have to stop and flush all those pages back to disk. It's almost exactly like the Java garbage collector. When Java's doing garbage collection, it has to lock that memory that it's collecting because we can't have a situation where the garbage collector thread is like cleaning out that memory and releasing it back to the heap. And then suddenly like some other thread modifies that memory. We can't do that at all. So memory gets locked when Java is doing garbage collection. Same thing here. If I'm flushing the dirty pages back to disk, I got to lock those pages down. The memory part of the pages, I got to lock that memory so that no one touches them. It's all overhead. Like there's no work being done here. This is all accounting. There's no real work. That code tends to be really, really, really tight because it runs constantly, just like the scheduler. It runs all the time. and it's not doing any real work. It's just moving stuff around. And so we need it to be really tight. Tight meaning fast. There's going to be a set. So this set, the non-paged pool, that's going to have stuff in it that is called wired. So that wired is, it's locked in place. The kernel sets that up, at various times, but then it marks it non-pageable. It essentially is locked into place. Nobody can touch it. And I was actually surprised that that's a term from Microsoft. They call that wired memory. But it turns out that Mac does the same thing, Mac OS. So if you look at the activity monitor, this is the memory portion. You'll see down here, I've got wired memory. I got 2.5 gig of wired memory. That wired memory is the kernel's memory. And actually, it kind of makes sense, right? Because I got 8 gig in the box. That's a quarter of that. So roughly a quarter or so, that top piece, that's wired memory for the kernel. No one's touching it. And I was actually shocked when we pulled this up. I was shocked to see the compressed number. Like, that's a really, really, really old technology. I remember back in the DOS days, before Windows even came out, like we had machines with 4 or 8K of memory on them, just really, really small. And if you wanted to store something that was relatively large in memory, we would zip it. You'd literally compress the stuff and then stick it into memory, and you'd have to uncompress it as it came back out. It was really crude, but I remember the commercial products were called like, memory doubler and stuff like that. And to see that the same technology is being used in Mac OS just really surprised me. But that stuff is going to be, that's going to be data that just isn't used all that much. Stuff the kernel needs or application needs, then maybe it writes it and then just doesn't see it again for a while. Like, why have it take up space, right, if I can compress it? And that question is going to be, how much time does it take to decompress and compress that memory versus how many times am I accessing the memory? Like, what's the cost on either side? And I guess I have to relate speed with space. Like, that's a weird equation. Anyway, that's wired memory. So, the nice thing about this is that pages in the pool, like, they're most of the clean pages are free, right? So if a process needs more pages of memory, you can just go get them from the page pool, the clean stuff. And what happens is the working sets grow and shrink sort of as the process runs. And so that page pool is constantly being refreshed. And the one non-page pool we just talked about, that's the wired stuff. You'll find buffers up there. So like the network cards, the wireless stuff, or the hardwired network, that sort of stuff. As bytes come in, they've got to be written somewhere. They go into this wired memory. There's going to be buffers up there for network and video and so on. All right. And we can just use this for reference if we need it. So that's kind of, that's a quick recap. And virtual memory is a cache. The other nice thing about this is that, did I even mention this? I must somewhere. Yeah, this could, I'll talk about in a sec, I think. Yeah, program administration, great. Let's talk about virtual memory as a memory manager. So this is the part where the process gets this nice clean memory space to work with. It also allows us to do stuff like this. Like there's a library called libc. That's the runtime library for C. It's essentially all the stuff that you need to run a C program. Well, as you can imagine, like practically everything on the system is going to reference libc at some point. Let's say I've got 100 applications running, 100 processes, and they all use libc. Does it make sense to have 100 copies of libc in memory? Like, no, right? So instead, what I'm going to do is I'll have one copy of libc. I'm going to map it into physical memory, and then I can just relate that back to every single process. So that stuff is going to live here. This region, this memory map region for shared libraries, that's part of the process's virtual memory space. But what's going to be in there is stuff like libraries, library code that everyone's using, they're sharing it. Or maybe I've got, let's say I've got two processes that need to talk to each other in some way. One way to, actually a really clean way to do it is to map in a page of memory into both processes. So they're both going to see it. And now they can talk to each other through that memory because that memory appears in their virtual space. Both processes, it's really just one physical location, but because they're mapped into both processes, if I write something here, I can read it in the other process and vice versa. So it can be a communication conduit between two processes. Here's the mechanism to do it. So these are just page tables. Here I got a page table for process 1, there's a page table for process 2. And if they both are using like libc maybe, or they're using a page to between each other, all I really have to do is write a page table. These are both kind of page tables, right? So write a page table entry for, looks like virtual page 2 points to physical page 6. The other process, virtual page 2, points to physical page 6. And now they both see that physical page of memory. So it literally is as simple as writing a page table entry. And there's a system call called mmap, memory map, that like sets all that up for us. We can say mmap this region, and it'll map it into a process for us and update the page table entries appropriately. How about linking stuff? The nice thing about linking is that, remember the ELF format, that executable and linkable format for files? That was kind of the executable file format that we looked at. All that stuff lives in the same spot. Like here, there's our process view of memory. All the stuff down here in the yellow portion, and then this sort of lavendery lilac-y portion up here, it all starts at the same address every single time. Now, some stuff is randomized for it, like, for example, the user stack. The top of the stack is random within a few hundred bytes, and they do that just to make it really hard for somebody attacking this program to guess where the stack starts, because the stack is a conduit into a hack usually. Like most of the low-level hacks are attacking a stack at some point. So if you don't know exactly where it starts, it makes it more difficult to attack the stack. So that's random. But these guys down here, the read-write segments, the data portion, the text portion, that's the code that's going to run. RO data is, if I create a string, for example, that goes into the read-only portion. Those start and end at the same spots every single time. And so it makes it really simple for linking or loading something in. Like every process looks exactly the same, right? And so the linking code doesn't have to do a lot of thinking. There's another CS t-shirt for us. Linking, don't do thinking. Like linking doesn't have to think of much. It just maps a page that exists in the ELF format. Oh, here's the text section. Where does it go? Oh, it always goes to this virtual page. End of story. Like you just map it right in, right? So linking is relatively simple in that case. How about initializing a program? I'm going to start up a program. It's probably going to be a system call to exec that does it, or execv. What it does is to set up that virtual memory space to begin with. And really all it has to do is, and this is part of everything starting at the same spot, it really just has to say, oh, I'm going to run this program from, it's going to be on disk to begin with. So exec sets up a page table for the process. It marks page table entries for things like the text portion, that's the instructions that are going to run, the data portion, which is all the initialized data and so on. There's an entry in the page table for those, and then the valid bit is set to 0. The valid bit indicates whether something's in memory or on disk. If it's 0, it's on disk. If it's a 1, it's in memory. But really all exec has to do is set up the page table, mark all those as zeros, and then transfer control over to the process. Well, the process, the first thing it's going to do is try to execute its first instruction. Where is its first instruction? It's the first couple of bytes in the text portion of its space. Well, it's a memory reference, right? So we go and look up that memory address. Oh, the valid bit is 0. It's on disk. Page it in. And now we can start running. So program initiation is simplified by this virtual memory system too. It makes it really easy. Like, oh, I want to start up a program. I don't even have to load anything into memory yet. Just make a page table entry for it. And when it hits that, it's going to see the valid bit 0, read it in, and now it can start running. Again, mmap is that's the function that's used to place these things in the right spot in the virtual process. If I need heap, same idea. Like here's the heap over here. Where's my heap? Here it is. This little minty green bit is my heap there. So that's actually set up in a couple of ways. Exec itself, as it's setting things up for the process to start the process up, it's going to need stuff off the heap as just as a part of its execution. And so that first time something from the heap, there really is no heap yet. And we go out to this wilderness chunk and pull off a piece, like taffy, you know, pull off a piece of memory and map it into the process. And now I've got a heap. If I need to grow the heap, you know, to hold additional memory, like it's really easy to do, right? If I need to grow the heap, I just say, oh, sure, just mmap it in and mark it as invalid, and then it'll get either paged in or brought in from the page pools. What else can we talk about? Oh, protection. How about that read-only data portion? So you guys, a couple of you ran into this problem a couple of times. If you do this, or maybe this is a better example. You do that, and then you try to do this. If you try to run strtoc on foo, it's going to crash. There'll be a segment violation. And the reason is that when you did this, that's a string literal. That's treated by the compiler as read-only data. And it's going to appear in this section of your code, in the read-only data portion. Well, what makes it read-only? Like, it's just memory, right? Why? I mean, memory's memory. Why can't I change that value of foo? It's because it's been marked read-only. And we mark it this way. So here's, this is a page table entry. I'm going to add a couple of bits to it. The bits are access bits. So the bits here are read, write, execute, and also supervisor. Soup is like, who owns this? Is that a kernel page or is it not a kernel page? On every single memory read, I got to go through the page table. Well, while I'm in there, I can look at these bits, and then the memory unit, the memory management unit that is satisfying these memory requests can tell, oh, I just tried to do a write into an area that's marked no for write. Can't do it, right? That virtual page 0 is read only, no writes. That's where the RO data stuff is going to go. And if I do try to do a write into it, it's going to raise an exception. Hey, you just tried to do a write, you don't have permissions, you're out of here. It kills the process at that point. That's a segment violation. And notice that, are they different? I'm trying to see the one that might be different. 6, that's 6. 6 there is, yes. Oh yeah, here's one. So same physical page, right? Physical page 6, PP6, pointing down here. Here's physical page 6 over here on this process. They have different permissions. So this is, actually this is a kernel sort of thing mapping that page in for some reason. I don't know why it would do that. So it has permissions to do a write. This process I does not have permissions to write. So it's a per process thing. Makes sense because the page tables are per process. There's a page table for every single process. So that memory management unit that I keep mentioning, it's a chip. There's a piece of hardware on the computer, on the motherboard, that gets involved in every single memory reference. Anytime you reference memory, it goes through the MMU, and the MMU has access to all the page tables. It's going to figure out, because it's going to work with virtual pages really, I've got a virtual reference here. Its job is to figure out where in physical memory that reference is and then return or modify the data at that physical spot. That supervisor bit, for example, like it's going to check that. If I'm trying to access memory that I don't have access to, like there's a supervisor bit there and I'm a user level program, I'm going to get a segment violation or an access violation. Those are those signals that you see when your program's crashing when you do things like dereference a null pointer. You can look back here. Where am I? 15. You look back here, see this little bit down here, this gray part that says unused? Well, what address is that? At the very bottom, that's address 0, right? So that's page 0. If I mark page 0 as like out of bounds for regular processes, if they try to access page 0, it's a segment violation. What's null map to? Null maps to 0. So if I try to access address 0, access or dereference a null pointer, for example, the memory management unit is going to raise that exception and the program's going to crash. It crashes, by the way, because at that point, the process is trying to work with memory that doesn't belong to it, and you don't know what it's going to do next. So it's kind of a preemptive killing. You don't even want it to execute the next instruction because you don't know what it's going to do. So you just kill the process, terminate it immediately when it raises that access violation. Are we 12-ish? Sweet. Protection. Oh, we're up here. Nice. So that's the memory management unit. And let's see how the MMU like does translations. Like I just said, it's responsible for taking a virtual address and figuring out what physical page that is, or physical byte even. Watch this. This is fun. Let's say we've got 32-bit addresses. So this is 32 bits down here, ones and zeros. And let's also say that our pages are 4K. That's kind of the number we've been using all along. 4,000 bytes per page. It's actually 4096. Well, how many bits do I need to address 4,000 bytes? The question basically is, what's the log base 2 of 4,000? It's 12, because 2 to the 12th is 4,096. So that means that I've got numbers here from 0 through 4095, right? So I can address any of 4,000 bytes using just 12 bits. It's the same way as, if my addresses are 4 bits wide, or I have 16 addresses, right? So it's 0000, 0001, all the way up to 1111. That's numbers 0 through 15 in 4 bits. Same idea here. 12 bits, I got 0 through 4095. So if that's the case, I only need 12 bits to get to any of those bytes in a 4K page. I've got 20 extra bits. So let's use the 20 bits, these, can I do it this way? Yeah, let's use these magenta bits as a page number. So now I've got a page number and then a byte on that page. That's what really the address looks like. Instead of just treating this as one big 32-bit address and starting at 0 and 2 to 30 seconds is a big number. It's 4 gig, right? So figuring out like what number this thing is. Now I'm going to break it into 2 pieces. One part identifies the page. The second part identifies the byte on that page. This is a really common construct, by the way. We use this idea of a base and an offset all over the place, especially in the operating system. And this sort of notion of indirection, where I've got a table that I look something up in, and that gets me into another table, and that table gets me into another set of tables, and so on. We see that all over the place. It's just a really handy way to do stuff. So this particular one, I've got 20 bits on the left in purple here. And so that's a bunch of zeros and a 1, 1 at the end. 1, 1 is 3. So that is page number 3. And then over here on the blue side, excuse me, must be the vaccine. I wonder how many things I can blame on the vaccine. I guess I'll see you this weekend. Oh, honey, I'm sorry. I can't plant those, like the vaccine. Like, oh, it just hurts so bad. Awkward. So that's page number 3. What's my offset into it? Which byte am I talking about? 1101 is 13. So that's byte number 13 on page number 3. We'll use that scheme a lot. It's like the analogy I used in A1 was, I've got a set of cookbooks that I love. It's Cook's Illustrated, a magazine, but they're all bound. So I've got from 98 to 2020, it's 22 volumes essentially. Well, every one of those volumes has a page 10 in it. I have an index. If I want to look up a recipe, that's like my page table. I look up a recipe, it says, oh, it's in this volume on that page. So I'll pull the correct volume out and go to page 10. Some other recipe might be in this volume over here, page 10. So the volume is like the page number here, and then the offset is, where I'm looking in that book. I just realized, I wondered why I saw a couple of puzzled looks in A1. It's because I'm talking about books and pages, and it doesn't map onto this page idea over here. Maybe it wasn't the greatest analogy, but I think you get the idea. All right, here's the big scary picture. This is how it's done, at a high level at least. So I've got a page table, right? This page table is per process. Every process has one of these. Every single memory reference is going to go through the memory management unit. What the MMU is going to do is take a virtual address on one side. It's going to figure out where in physical memory that thing lives and then return the data. Here's how it does it. It goes into the page table. The page table looks up the page number. So that was this part of it, right? The purple part, the magenta part. So it looks up that. That gives me the page number. It's essentially the index into this table. From there, I get from the page number, like page 3, I go to the third thing down here. That tells me what physical page is mapped onto that virtual page. So that gives me the physical page. And then the offset is the same. So, if it was virtual page number 13, and then the byte I'm looking for is 5 or something, well, that virtual page is going to map onto a physical page, but it's still going to be 5 bytes in, whether it was virtual or physical. So I can just drop down that offset. But it's just going to use the page table to look it up. Grab for the page number from the first part of the address, look it up in the table, find the physical page, go to the offset, and then return that data. If the valid bit is 0, that's a page fault. We'll see that in a sec. Here's what it looks like if the physical page is in memory. So the valid bit is 1. Here's the virtual address coming in. So the CPU sends a virtual address over to the memory management unit. Give me the data at this virtual address. The MMU goes through this scheme, right? Figures out the virtual page number, and then the offset into that. Well, from the virtual page table, or the page table rather, I've got this valid bit. So it looks up the page, the virtual page. Oh, it's not, it is valid. This one's a 1. So it's in memory. Cool. Figures out, goes to the page table, figures out which physical page that data is on, uses the offset to get to the particular byte we're interested in, goes out here, that's actual memory, grabs the byte, and just returns that data to the CPU. That's if the thing is in memory. That's sort of the best case, right? It really is just doing a translation and grabbing the byte right from physical memory. If the valid bit is 0, so the thing is on disk instead of in memory, it looks like this. And it's not that much different. So the CPU still is going to hand a reference here to a virtual address. The MMU looks up the page, virtual page number, looks in the page table, and says, oh, shoot, the valid bit is 0. This thing is on disk. So that's a fault. So this is the page 2 and 3 is the page table lookup. That's an exception. It's a page fault. I got to go get it from disk. So it does it. Like it says, all right, I'll go grab it. This fault handler code, that's kernel code. That's just a little bit of code that manages finding the page on disk and reading it into memory. And then it updates the page table to mark the valid bit as 1. Now that virtual page is in memory, it's valid, right? So that's what the fault handler does. Another really tight piece of code, because faults happen all the time. Like here, we're looking at top in A1. Here's top running on this machine. Here's the fault numbers over here, that column. Like there's a lot of faults happening. Look at this number. Who's that? That's Docker. Thank you, Docker. Docker's a resource pig. Zoom's up here somewhere too. Here's Zoom faulting like crazy. So page faults happen all the time. A lot of page faults every second. It's got to be really, really tight code. Anyway, so the page fault handler runs, grabs the page from disk, loads it into memory, updates the page table entry, marks it with a 1, and then it just says, it sends a message back to the process and says, oh, why don't you try that again? And it says, all right, I'll try it again. This time when it tries, the page is marked as 1, right? It's valid, it's in memory, and so now it just looks like that. So really the only difference is, it's like, you ask the memory unit for a byte of data, and it goes, try it now. and because it's done all this stuff, right? Move the thing in, mark the valid bit as 1. Try it again now. And now when it tries it, you get the data back and everybody's happy. That makes sense? I think it makes sense. It makes sense to me. All right, let's talk about this thing. So when I'm doing this translation, right, I'm constantly hitting the page table. Like the page table on basically every single memory reference, I'm gonna hit the page table. It would make a lot of sense to put the page table in cache somewhere. The best place to put it would be level 1 cache. Remember that picture we looked at, was it on Tuesday, the picture of the CPU die? And I pointed out, oh, here's where the cache is, sitting on the CPU chip. That's level 1 cache. It's literally right next to the logic circuits of the CPU. You can't get any faster than, well, registers, but for caches, you can't get any faster than a level 1 cache on the CPU chip itself. The problem is it's really small. Those are like 1K or so, or 4K, and usually they're filled up with instructions. Like that's what we want in that cache is instructions, because the CPU is executing instructions. And so, I mean, page table entries are just regular memory, right? And so if the CPU is fetching something from the page table, it's going to end up in level 1 cache. It's probably going to get moved out pretty quickly. So it's not the greatest place for that data. It's a really good place, but not the greatest place. I wonder what that is. This is one of those tables that lifts up and down, I think. There's all sorts of gears and levers back here. All right, so we probably aren't going to end up with these things in level 1 cache on the CPU. And so instead, we'll take up some real estate on the memory unit, the memory management unit itself. That, again, it's just a chip, right? So, you know, it's got some die on it. I wonder if I can find one. I didn't try this in A1. Can I see a MMU chip die? Images. That's a CPU. That's an Apple ASIC. I don't see any offhand. 68030. Is the 030? No, the 030 is a CPU also. This is just showing me CPUs. That's too bad. Anyway, we're taking up some real estate on the memory unit itself for cache. So it's gonna be a little bit of cache memory sitting on the memory management unit. That's where we're going to cache the page tables. It makes perfect sense, or the page table entries at least, makes perfect sense because it's the memory unit that needs them. And so let's co-locate those caches right on the chip, right exactly where we want them to be. That just makes sense. So we're gonna put this cache on the chip. It's called a look-aside buffer, a translation look-aside buffer. It's really just a cache. I don't know why they give it such a fancy name. So the TLB, I guess it's easier to say TLB than cache, maybe? I don't know. So the TLB is going to be a group of sets, and each set is going to contain a sequence of page table entries. We're going to use the same idea we used before of taking part of the address and breaking it into 2 pieces. Remember when we did this thing? So we said, you know, the first part of that address is the page number, and then the second part is the offset. We're going to take that page number and break it into 2 pieces. So we'll have 3 pieces now. All right, we're going to take the virtual address and split it. Actually, I'll just show you the picture. It's easier to show you. Here's the picture. So this VPN up here, from here to here, not the VPO part, that's the offset, but just the address part. We're going to break it into 2 pieces. The first part of it, this part over here, That part. That part over there is going to be an index into a set. Let's say I've got 16 sets. How many bits do I need in the index? 4, right? Because 2 to the 4th is 16. So if this thing was 3, for example, I go down to set 3. If it's a 1, I go to set 1, and so on. So this index is going to be, which set am I talking about? The next part is going to be, which tag am I talking about? So that the tag part actually identifies a page table entry. So when I look at this virtual page number and I need to know where the page table entry for it is, I can just take the index, which gives me access to one of the sets, and then the tag, that gives me access to the page table entry in that set. It's exactly the same thing we did here, where I just broke this into a page number and then an offset. Exactly the same idea here. Now I'm taking a few bits here, that's going to be a set number, and then here is going to be the number of the actual page table entry based on a single virtual page number, a virtual address rather. It's an associative cache, right? So this means that anything I need to find in the page tables, all these page table entries, they've been spread across this cache, and I can use the virtual address to calculate which set and which offset in that set I need to get to read the page table entry. It's a really fast way of indexing into this cache. And it's going to use a least recently used replacement policy, which makes sense, right? Because if I haven't hit a page table entry for a while, that means I'm probably not accessing that page much anymore. Like, why keep it in cache? Cache is limited. I've only got so much real estate on that chip. And so just toss out the ones I'm not using recently. It turns out that the code that runs this stuff, it's actually hardwired like into the chip itself, the logic circuits. But the cache hit rates on the loci buffer tend to be in the 99% range, which means that when you look for a page table entry, 99% of the time it's going to be in cache. If it's not in cache, it's going to be on disk somewhere, which is not great. But 99% hit rate on a cache that's a good cache. That's a really good cache. Actually, it's the same with the L1 cache. The instructions in the L1 cache, that's a 99% cache also. I wonder if they use the same sort of algorithm. It'd be interesting to look at. I mean, once in a while, you're going to get a PTE in the CPU's L1 cache, just because it's just a memory reference. It'll show up there at some point. But really, the memory unit uses this loci buffer, its own cache that it manages itself. There might be a case where I need more than one table. Like, actually, somebody asked, who asked that question really early on? It was in A1. Somebody asked the question of, what if the page tables are really, really small? Like, maybe each page table only holds, like 4 pages or something. Like basically my page size is really, really tiny. My page size is, 16 bytes or something. I'm going to have a lot of page table entries because I've divided this big piece of 4 gig memory up into 16 byte chunks. To address each one of them, I'm going to have a gazillion page table entries. I mean, that's kind of an extreme example, but what if I need to do that? Well, I can just keep using this idea, right? I can take that part of the address, like here, I can take this thing, and instead of like page number, I can say, you know what? All right, so those they're going to identify a table that is a group of page tables. I've got 4 bits here, so I get give me access to 16 new tables that each have however many bits this is. How many bits that is? 2, 4, 6, 8. Let's say it's 10. So each of those 4 tables would have 1,000 entries in it. And then I can use the next set, to identify yet another set of tables. So I can use this idea of just taking parts of the address, like here, like first 4 bits, that gives me the highlight, the first lookup. Once I'm in there, use the next 4 bits for the next lookup, and so on. So I can go from table to table to table until I get down to the physical page I'm looking for, and it's page table entry. Here's a picture with two layers. Nothing fancy here, right? So I've got page table entry here. So the first couple of bits gets me into this set of page tables. Here I got, it looks like 1K, right? So I got these things in each of these indexes into 1,000 of these. Each of these indexes into one of these. Maybe stick another table out here. So I've got, break this thing on the left into 4 pieces, and I get 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. So I got 4 of these. All I'm really trying to do here is to save space, because what's going to end up happening is some of these page tables are not going to be used much, and I can just page them out. If I just had one big page table, I'd probably have to keep the whole thing resident in memory because I'm using it so often. I don't want to keep the whole honking thing in memory. Just break it into pieces. Some of the pieces will be on disk, some will be in physical memory, but I can use that first table to index into the one that I need. Yeah, for example here. So table number, page number in that table, and then offset off of that. And again, that's something we use all over the place. Like I've written tons of code in my career where I'm using bits like that to break things into chunks and then address those chunks, and each of those chunks, addresses some other set of chunks and so on. Like that, I just do that all the time. Maybe it's just me. I blame it on the vaccine. All right, bottom line. So bottom line is that we can think of this as a big cache for stuff on disk, virtual memory, as sort of a cache for programs sitting on disk. And just think of all the advantages that virtual memory gives us, especially that nice, clean, contiguous space for every single process. It also helps us manage physical memory too, because I can move pages now in and out from disk back to memory, back to disk. I can do all of that behind the scenes. The process doesn't know what's happening. All the process knows is it's executing instructions one after the other. It's accessing data within its process space. It doesn't realize that those are fake addresses, and there's all this other stuff happening behind the scenes to give it the data that it needs. I mean, that's a beautiful thing. That's one of the few layers of abstraction we have at this level of the operating system, but it's a perfect abstraction because it gives such a beautiful, clean, perfect view of the address space to the process. And meanwhile, the kernel is like juggling stuff behind the scenes, but we don't care about that, right, from the process standpoint. We can use it for permissions. We can use it for caching. We can mark things read-only because we're using these page table entries now to access memory, and we can put all that stuff in the page table entry. And also, this is really, really fast because it's done so often, and like it's just, as I said, overhead. All right, and don't forget the wired stuff doesn't get paged. That's all that non-paged pool stuff. All right, guys, that's all I've got for today. Looks like we're almost out of time. So that's it. I'll work on PS5 for tomorrow to get that out to you. Other than that, like, there's not much to do, right? This weekend, for this course at least, like, just enjoy the weekend for once. Like, go have a nice time on the weekend. I hope you're not busy in your other courses. Oh, 131, so sorry, so sorry. All right, well, good luck on the exam. I'll talk to you guys later. Peace out. See you Tuesday. See you Tuesday. End meeting. Thanks, you're welcome, you're welcome.